My name is Dr. Brian Pijanowski. I'm professor, Department of Forestry and Natural Resources at Purdue University. My background is in landscape ecology and GIS. I'm the lead developer of the land transformation model, developed the first version of it in 1994, and I've published over 60 articles that explain how it's used. What I'd like to do in this talk is provide you with a little bit of a background on what are models. Second, how does the land transformation model work? Third, I want to provide you with a summary of the output of the model, and then finally give you some advice on how to work the model output. Background on models. So what is a model? Well, most scientists will define a model as a simplified representation of reality that allows people to understand complex relationships of the factors that are of interest. Because it's a simplified representation of reality, we can say that all models are wrong, but many are very useful. What kinds of models exist in science? We generally have about 4 different kinds. These include conceptual. These are outlining the relationships between main components in a system using box and arrow diagrams. A second is graphical. These illustrate the relationships between key variables in a system. Mathematical. These are probably the most famous kind of models. Isaac Newton developed some very simple equations for how the universe works. A final kind of model is an empirical model. These are models that are based on data, and these are, for the most part, statistical models, but we'll see here in a second that the land transformation model, which is an empirical model, is not necessarily a statistical model. There are a lot of challenges to developing models. First, data are often lacking for the key variables that you need. Data are collected at different scales than what you need, or different scales in which you need to integrate them within the model. Data quality can actually be fairly poor or undocumented. Models are oftentimes for general use, and many times we need to use models for very, very specific purposes. The time it takes to get a model together can be a long, long time, sometimes years, and oftentimes you need to make a decision that afternoon. And then finally, model assumptions are not often very transparent to users of the model, so modelers have to do a much better job at describing what those assumptions are. So let me tell you how the model works. First of all, we use a lot of GIS data layers to build the model. These include layers related to roads and rivers and other kinds of features. We use the GIS to calculate distance to roads across an entire community, distance to previous urban. Urban is a main driver because it's fairly inexpensive to build out from that current urban infrastructure. Distance to surface water. People like to put their houses next to water. We also use historical land use maps and then feed both of these in to what's referred to as a neural network. It's a form of artificial intelligence that learns about patterns in data. It first looks at the data using kind of a random pass at it, but eventually it learns about patterns that fit the best. And then once we find a good fit, then we save that and use it to build a model, a map of locations of high priority for conversion to urban. Now, how do we forecast that into the future? Well, we have to figure out how many new people will be coming into a community and what that will mean for the amount of urban in that community. We do a historical assessment. We ask the question, how many urban pixels or how many square kilometers of urban is needed for every 1,000 people that move in? And we use that demand model to be able to forecast forward. The final output of the model is a bunch of maps of time steps into the future, of future urban change on top of the existing land use map. Let me show you a little bit of the data that we would use to build the model. These are 3 counties in northwest Indiana. We would calculate, we do calculate count distance to county roads, distance to primary roads, distance to secondary and connecting roads, distance to primary roads without access, distance to current urban, distance to rivers, and then occasionally we use the slope of an area to be able to have the neural network learn about patterns of change. The change maps can be from a variety of sources. We normally use the National Land Cover Database. This is a 30-meter database developed from NASA's satellite remote sensors platforms. This is showing in northwest Indiana land use cover change for a 15-year period between 2001 and 2016. And here you can see that there's a lot of change that's occurring in these northwest counties. Some patches of change are big and some are very small. We also tell the model areas where land use change cannot occur. These include parks and protected areas, lands and trusts. So here is the National Lakeshore right up here in Porter County. And all these other areas located in black are areas where we don't have any change that will occur into the future. We call this an exclusionary zone. The population demand model is developed for every city in the country. We develop a city boundary map using GIS. So this is a community-based growth model. We've developed 4 of them, and then we selected the very best one to use in the final product. This gives you an illustration of how the neural network is actually configured within the software. So we have what we call these driver maps, so distance to county roads. For every pixel in our map, we have a value. These values are then passed through nodes and connection points here that have values through a hidden node and eventually to an output node where we tell it change or no change occurred at that location over a historical time period. So let's take a tour of the model output for Northwest Indiana. What I'm showing you here is a map of the land use land cover from the 2001 National Land Cover Dataset from NASA, zooming into a particular area of high urbanization that will occur over the next 30 to 50 years. This is all shown here in pink. The red is urban in 2001. So you can see that the model is forecasting lots of expansion from existing urban, but you can also see that the model is predicting some small little patches of urban out in the rural areas. So the neural network has learned about the spatial configurations of the drivers and the spatial patterns of change across this area and then projects it out into the future. So one of the things that you should notice here is that a lot of the projections are in not the most realistic shape. So a lot of them are like round circle blobs. You just have to interpret those in the future as kind of square or maybe rectangular shapes. The model is not able to handle the shape parameter for growth at the moment. So here are some thoughts on how to interpret the model, and really a summary of some of the model assumptions. First, what the model has learned about the past is what it knows only about the future. So it's learning from historical patterns, and the future is simply going to look very much like the past, which I think might be a reasonable assumption for most communities. Second, rates of past change are applied to the future as well. In other words, if your community saw 10 to 15% growth over a course of a decade, which is about average, then you will probably see that in the future as well. Data quality is, we're assuming that the data quality is perfect, although the neural network actually does really well with noisy data, so it's not a problem. Statistical models tend to be very sensitive to noisy data. I also say that we shouldn't sit around and argue about the pixel, the location of a pixel, because the model really can't predict at 30-meter resolution with 100% precision. What you need is a tool that helps you to guide your thoughts, and it generalizes the trends about the future, and it actually does it fairly well. And of course, the model can't predict unusual events like pandemics and stock market crashes and interest rate blips. It's kind of looking at long-term trends and averaging those out and putting them into the model and using those as forecasts into the future. Thank you for listening to the Lightning Talk on the Land Transformation Model. Again, my name is Brian Pijanowski. You can reach me at this email address, or you can visit tippingpointplanner.org for more information about how the tool is used and how the model exists within some of the planning components.